So Tim, I'm a software engineer at Julia Hub, where I'm mostly working on GPU backends. And today I'm going to give yet another talk on GPU computing, but I'm going to go back to the basics and focus on what are GPUs, why you should be interested or you could be interested in using GPUs, and how you do so in the Julia programming language. So again, back to the basics. So let's start with what GPUs are. And essentially, a GPU is just a massively parallel accelerator that consists of multiple CPUs, multiple dedicated processors, which have fairly simple control logic and cache, or at least simple compared to a traditional CPU, but have a very large register file and lots of ALUs. The result of that is that whereas on a CPU you have few but very powerful threads that can execute general purpose code, on a GPU you have a massive amount of threads which are much more lightweight, so you cannot use them to execute operating system code, for example. It's a very constrained set of code you can execute on that. It's not general purpose. And in order to feed all of those threads, we have a fairly high bandwidth memory bus that, of course, has a fairly high latency because it's optimizing for the one or the other. So why should you use GPUs? Well, because probably many of you are doing scientific computing, and scientific computing is a fairly good match for GPUs because oftentimes we have lots of data, so lots of implicit data parallelism. But we also perform sufficiently complicated computation that makes it possible to hide the latency of the memory bus. And because of that, all of the major vendors have their own software toolkits to use a GPU for computing, for general purpose computing. With NVIDIA, we have CUDA, AMD has ROCm, Intel has one API, and with Apple, we can use the Metal APIs to use a GPU for computing. Of course, all of these toolkits sadly use a low-level language, so our next impulse is let's switch that out with Julia. And Julia is actually fairly well positioned to be used for GPU computing. On the one hand, it's a high-level language, meaning it's more productive than the low-level languages you would use as part of the vendor toolkit, but also because Julia is ultimately a compiled language, which makes it possible to write our own kernel code, because Julia is compiled down to fairly efficient machine-native code, which again is one of the requirements for using these lightweight threads that a GPU processor has to offer. And nowadays, for all of the major vendors, we have packages that make this possible. We have, respectively, CUDA.gl, AMD GPU.gl, OneAPI.gl, and Metal.gl. And all of these are built on a similar stack and have a similar set of founding principle features as you want it. The main one is that it has to be user-friendly. However, we want it to be user-friendly without sacrificing the performance and the flexibility that a GPU has to offer. We generally, in order to do so, offer you multiple programming interfaces, one high level, one low level, and we also make it possible to some extent to write portable applications with each of these programming interfaces. So let's zoom in briefly on each of these. User-friendliness is paramount. It should be easy to use a GPU. And one of the main things we do is simplify the installation of the software you require to use a GPU. So we still have some dependencies, of course, because of, for example, administrative privileges to install the NVIDIA driver. But other parts of the software stack you require, we automatically distribute using Julia's artifact subsystem. So here you see basically how you start using CUDA. You just go into Julia Package Manager, you do add CUDA using CUDA. It will automatically detect the driver you have installed, download everything it needs of the CUDA toolkit, deploy it in your private Julia depot, and use that for the remainder. And the other backends have something similar. Another way we try to make GPUs much more user-friendly is to provide some more sane defaults. For example, in the case of Metal, you normally have to look up the device using API calls. You have to create a command queue and use that to queue objects on. Whereas in Metal.gl, we just make it possible to import a package and do add Metal of a kernel function. But again, it's not because we make it user-friendly that we sacrifice that flexibility. It's still possible to use those lower-level APIs to look up your own devices and to do your own command buffer management. But the main goal is here to make everything as user-friendly as possible and make it a bit easier to get started. The other point was multiple programming interfaces. Broadly categorizing, and you can speak about the application level, the array level, and the kernel level. The application level of using GPUs is when a piece of software has a magical GPU flag. Like, for example, Flux does. It has this GPU function, and you just call the GPU function on your inputs, on your model, and then everything will execute on the GPU. That's not terribly interesting for this talk because it's application specific. So I'm going to discard this level and move on to the main interface we offer to programming GPUs, and that's arrays. Essentially, all of these array packages, all of these GPU packages implement a similar array programming interface where you just import the package, you create some data, you upload it to the GPU by using a GPU array type, and then every operation you call on that GPU array type will be automatically optimized thanks to Julia's multiple dispatch functionality. And the goal for these types is to be as compatible with the base array type as possible. So you can do lots of familiar operations like create a view, compute a sum, do multiplication, adjoint, and so on and so forth. All of these are going to be implemented in some way or another with GPU compatible or GPU optimized functionality. Sometimes we even integrate with external packages. For example, again, example from CUDA.gl. If you call code from random.gl, we'll call into current. Linear algebra will use cuBLAS. Sparse array will use cuSparse, and so on and so forth. Some of these details differ a bit between the different GPU packages that we have, but nonetheless, again, we try to be as compatible as possible with the CPU array type so that you can conveniently write code for the CPU and then port it to the GPU. The main power of Julia, however, comes from these higher order array abstractions. And that sounds complicated, but it's basically an abstraction, a function that takes another function as an input. For example, the map function. The map function, you pass a closure, an anonymous function that you defined, performing some element-wise computation. And this is extremely powerful because it composes this library definition of the map function, which is a GPU-optimized implementation, with some user code. And this is only possible because we have a JIT compiler, which is possible at runtime to generate custom kernel code that involves these two pieces together. And this is so powerful because typically other languages are restricted to what libraries have to offer, what the library has been compiled for. Whereas in our case, we can create generic definitions, compose them with your code, with your types, and generate new specialized kernel code. Some other examples include the broadcast function, which is also going to perform JIT compilation, functions like reduce, accumulate, find first, and there's a couple of those. And to show that this is pretty powerful, here's a very tiny example I took from this course, implementing a simple linear regression model. Again, I didn't write this, just took it from Discord. But the magical thing is, to run this on the GPU, we just change the inputs to CURay. And all of the array operations are automatically going to dispatch to a CUDA implementation. And the result even scales favorably. I mean, this is not going to be a very high-performance implementation, but nonetheless, it's a very good starting point to take some code that you developed and accelerate bits and pieces of it. Of course, as I mentioned, it's a good starting point. It might not always be sufficient. Sometimes you need some operation to be implemented faster or more flexibly. And for that, we offer a lower-level programming interface, and that's the ability to write your own kernel functions. So here's a simple kernel definition in Julia. Well, actually, this is only the kernel definition. A kernel is a scalar function that gets executed on the GPU in a massively parallel fashion. So a kernel function is responsible mostly for computing a single element. And in order to differentiate the computation, we use indexing intrinsics. For example, here, my kernel function is going to look up what my current thread number is, and I use that to determine which element I need to be computing. And then on the host, we allocate some data, and crucially here, we launch our kernel function in parallel. And this is the same code for doing so in CUDA-C. And as you can see, the host interactions, like allocating memory, are greatly simplified. As I mentioned before, we try to make it as user-friendly as possible. On the other hand, the device code is actually fairly similar. And this is also intentionally, because we still want to make it possible to use a GPU for what you bought the GPU, namely to get all of the performance out of that device. And as such, if we would put too many abstractions in the kernel code as well, it would not be possible for seasoned CUDA developers to take CUDA.gl and to use the GPU as they want to. So again, we want to retain all of the flexibility that you require. Nonetheless, kernel programming is still always a more advanced level of programming. The arrays should always be the starting point. And it looks the same with other vendor packages. Sometimes we deviate a little from what the vendors normally do. For example, in Metal, you have to pass the thread number as an argument, whereas for consistency's sake with all of the Julia backends, in Metal.jl, we still use a function. OneAPI.jl actually requires you to use these parallel intrinsics, while again, we do something that more resembles OpenCL, again, for consistency's sake across all of the GPU backends, such that if you learn CUDA.jl, you'll find your way around in Metal.jl and in OneAPI.jl and in one AMD GPU.jl as well. Generally, we support a set of features in kernel programming land that makes it possible to implement all of the kernels you'll need. For example, we have these indexing intrinsics already mentioned. You have shared memory, which is a memory that's shared within each of the single processors of the GPU, which is faster than always going to global memory. We support subgroup operations, which are advanced intrinsics to communicate between threads, and we support atomic operation. And with those two features, which are again supported across all of the backends, you'll be able to implement a wide variety of high-performance kernels. However, if you need more advanced features, again, CUDA.jl supports much more of the CUDA C standard because it is just a much more mature package. And to show you what the JIT is doing behind the scene, you can actually use these very similarly looking macros. So in Julia, the interactive utilities standard library has these add code underscore LLVM and so on functions. Well, we have the same with the GPU compilers, but they're called device code because we're generating code for the device. The native code for CUDA.jl is PTX code, so this shows the generated PTX code for our vector addition function I defined before. And as you can see here, this is pretty highly optimized, very clean scalar code, just as you want it for the lightweight threads that the GPU has to offer. In the case of Metal, we have add device code AGX, and this is actually based on a reverse-engineered compiler that the Asahi Linux guys wrote for their port to Apple M devices. And in the case of OneAPI, we generate SPIR-V code. Looking at this code may be interesting in order to either look what the JIT is doing or to optimize your code and, for example, spot exceptions or other code patterns that you don't want in your generated code. But generally, the better way to do so is by benchmarking your kernel. And this is something important to mention because what I'm doing here, for example, allocating some memory and then doing a broadcast addition with the reverse of my array, both of which are operations that execute on a GPU, timing this as such is wrong because those operations execute asynchronously. There's no reason for the CPU to wait for the GPU to finish computing. Every operation that we enqueue on a CUDA array generally is asynchronous. So this timing is wrong. We actually need to add a CUDA.addSync, which will make the CPU wait on the GPU to complete, and as such, this timing, this benchmark will be correct. CUDA has some helper macros for that. For example, you can do CUDA.addTime, which will also give you the amount of GPU allocation, so that's convenient. But generally, the recommendation is still to use benchmark tools, which gives you much more statistically sound measurements. For the same reason, you cannot profile GPU code. You have to use vendor-specific profilers. Nowadays, CUDA.jl has one integrated, so you can do CUDA.addProfile, and you get a very nice view of everything that happens on the host that's CUDA-related and everything that happens on the device. And our other backends have something similar, but powered by external tools. So CUDA also has these external tools by NVIDIA, which is Nsight, which gives you the same information, but in a nice visual timeline. Metal.jl has Xcode, AMD.jl has RockProf, and OneAPI has VTune. But to make this all a little more concrete, let's jump into an example. And for example, let's say we want to implement this root mean square error computation, taking the root mean square error of two matrix inputs. Implementing this in Julia with array operations is pretty simple. We can just write this expression. So RMSE of A and B is the square root of the sum of the difference squared divided by the length of our inputs. We can run this on the CPU, and we get a pretty slow 3.5 millisecond timing. And again, porting this to the GPU is just as easy as switching the inputs time, and we get a very nice speed up. And of course, this speed up is in a way not fair because we're not timing the time it takes to transfer the memory, but most of the time that's not relevant, so I'm discarding this here. 2 notes. I'm not using CUDA.addSync here. That's because we're reducing to a scalar here. And as a result, the CPU has to wait for the GPU anyway. Now, I'm just adding this here as a note. Generally, it's fine to always add CUDA.addSync to a benchmark invocation just for safety. Another thing I'm doing here is a CUDA.allowScalar, which disables scalar iteration. And this is something that happens when you try to invoke some abstract array fallback code, which uses for loops to compute something element by element on a GPU array. And in that case, it's not actually using the GPU, and as such, that's very slow. Using this call, you disable these kind of fallbacks, and it'll throw an error instead, indicating you that some operation wasn't implemented for the GPU. And then you can either file an issue or look into how you differently execute that operation in a way that's GPU compatible. Now, optimizing these kinds of expressions is something that's typical Julia optimization tips and tricks, like pre-allocating your outputs, preferring in-place optimizations, fusing operations together. And as an example of the last one, so this was, oh, this is not readable, that's a shame. What I'm doing here is, well, let's go back, it was legible here. So here I'm doing A minus B. If we make this A dot minus B, we're actually going to get a single broadcast expression for those 2 operations. As a result, you're going to have fewer kernel launches because this operation will be computed using a single kernel. And the performance goes from 57 microseconds to 42 microseconds. You can see the dot here. And we can take this one step beyond. For example, we can fuse the entire broadcast into our reduction. Curiously, this slows down on the CPU, but we only care for the GPU for this talk, and it's sped up again. And importantly, this optimized implementation here, that's still very generic code. That's still code that can execute with a Q array, with a rock array, with a CPU array. It's very generic array code. And this is something that's crucial because if you write code and optimize code like this, your code can be reused in a variety of situations. It can be used on the GPU, it can be used on the CPU, it can be used on a distributed machine just because of the generality of these array abstractions. And generally, the recommendations here are, for example, to use broadcast and other array abstractions instead of for loops because of GPU compatibility. If you need to allocate an output container, use the similar function. Don't just allocate a CPU array because then you would be mix and matching CPU and GPU inputs. If you need to dispatch on the array type, use abstract array. If you create a struct, make sure that your fields are not typed array, but make them abstract array or parameterized. So a bunch of these make it possible for your code that's been written in this generic Julia fashion to be reused across situations. And for a silly example, here I'm just creating some user code, and then I'm using the map function to execute that code on some GPU inputs, but I'm also computing the derivative of that, and I'm doing this on multiple GPUs on multiple systems at the same time. So this is it's a little of a contrived example, but it shows if people write packages in a very generic fashion that it can all be composed together and used together in situations that you might not have originally thought of. So it's very valuable to go to extra mile and to write generic array operations instead of CPU or GPU array-specific ones. Now let's do the inverse, and let's write a kernel function, which is going to be completely specific to CUDA.jl. So again, we're implementing this root mean square error function. I have some host code here that takes my A and B inputs. And then here I have my kernel function, which for a very naive implementation, every thread is going to take a single element, compute the difference, square it, and then atomically write it into a single output cell. And what can we see? That this is extremely slow. And this is just to show that writing fast GPU code isn't trivial. So if the array operations are fine for you, then by all means, you should be happy at that point. If you want to write a custom kernel in order to optimize things, you'll have to know how a GPU works. For example, in this case, it's extremely expensive that every thread is doing an atomic operation to global memory. So we can optimize that by having every thread process multiple elements by putting a loop in our kernel function and then doing only a single atomic operation for every thread instead of for every element. And this already improves performance to 50-fold. However, it's still slower than our array operations, but we can go beyond. For example, instead of having every thread do an atomic reduction, we can actually do a parallel reduction within shared memory, such that only every block has to do a single reduction. And this is pretty complicated, also overflows my slide apparently. It's just to show that CUDA.jl makes it possible to write these high-performance implementations by using all the tips and tricks that the GPU has to offer. And at this point, we're actually exceeding the performance of our array operation-based implementation. So it can definitely be worth it to write your own kernel functions for performance, for flexibility, or for whatever reason you require. Of course, at this point, we have a kernel that only works on CUDA.jl. So if you need something that's portable, you can have a look at the kernel abstractions package. Kernel abstractions.jl defines a domain-specific language, if you want it, that abstracts the kernel programming APIs that the different backends have to offer. For example, instead of shared memory, we have at local mem here. Instead of the thread IDX function, we have the at index macro, and so on and so forth. So anyway, kernel abstractions is the common denominator of all of the kernel programming functionality that our GPU backends have. And as such, it's also a bit less flexible. So the loop, for example, that grid stride loop, there's no nice ways to currently implement that in kernel abstractions. So I've removed it, and as a result, performance has regressed a little bit. On the other hand, this implementation works across all our GPU backends, as well as the CPU. So this can be a very valuable target to use as a development platform. And in fact, it is possible to use kernel abstractions to write very high-performance kernels. This chart was also shown by Chris this morning. It's how some differential equations functionality was written in kernel abstractions.jl and run across all of the GPU backends that we support, resulting in pretty great performance, outperforming competitors. In the interest of time, I'm going to stop here. So just to summarize, scientific computing, if you're doing scientific computing, GPUs can be a very great platform to use to accelerate your code because of the data parallelism and the inherent complexity in there. And Julia is actually a great language to do so. On the one hand, because we have these very high-level, user-friendly array operations, but also because we still give you all of the flexibility that you need to implement your own kernels and to optimize whenever you need it. And at this point, I would just recommend you to try it out. Many of your laptops will have a GPU that's supported by any of our platforms, so let us know how it works. At JuliaGPU.org, we have a website with links to all of the individual backends. We also maintain a blog where we once in a time post something about new versions of packages and so on and so forth. And we also have a bi-weekly office hours, which is on the community calendar. So if you have any questions, feel free to drop by there or on Slack on Discourse. Thank you.
Thank you. So that leaves us with some time for some questions from the audience. We have one at the back.
Thank you. So yeah, thanks for the nice talk. For the average Julia package developer who just uses GitHub Actions to test their code, sometimes it's a bit hard to check whether GPU support is broken or not. Have you considered maybe implementing some sort of dummy GPU type which actually runs on CPU and therefore would work on GitHub Actions, but disallows things such as scalar operations?
We actually do that. As part of GPU arrays.jl, we have the JL array type, and nowadays it's also put in its own package, jlarrays.jl. It's not fully fleshed out yet, but it does support what you mentioned, namely disallowing scalar iteration for operations that aren't supported. The general problem there is that it sometimes differs between packages what is and isn't implemented. Some kernels are only implemented in CUDA.jl. Some libraries are only supported by some of the vendors. So it is impossible to give you one array type that will tell you which of the GPU backends it will work with. However, if you restrict yourself to what's implemented in GPU arrays.jl, which is this package that implements a variety of operations in a way that's supported by all of the backends, in order to test against that, you can use the JL arrays package, which you can then similarly disable scalar iteration for.
Okay, thanks a lot.
Any more questions from the audience? All on the other side again. You do this on purpose, right?
Thanks. Sorry. During your talk, you focused mostly on vendor-specific GPU backends, but do you also support like vendor-agnostic GPU backends like Vulkan?
Like Vulkan?
Yeah.
For Vulkan, we currently do not support a compute array type. There is a Vulkan.jl, but that's completely focused on the graphics side of things. We currently do not have a single package that does automatic vendor-neutral array abstractions. There is one effort by Intel, actually, the unified runtime, which is an abstraction of all of the compute platforms below it, and we're looking into wrapping that in Julia, so that would give you what you want. But the problem with Vulkan is that the code generation parts generally are not supported for kernel compilation by all of the backends. At least for a very long time, NVIDIA only supported compiling graphics kernels via Vulkan, and I'm not sure whether that situation has changed or not recently. So, summarized, currently not, might change in the future.
Thanks.
Any more questions from the audience?
I know in the past there was a OpenCL.jl. I'm not sure if it was ever stable. What's the status there in terms of vendor agnostic?
The problem with OpenCL.jl is that it relied on a different compilation model. So in a way, it actually comes back to the same problem with Vulkan. There was no way to conveniently compile Julia code to an intermediate representation that was supported via OpenCL by all of the backends. So OpenCL.jl back in the day did that by transpiling Julia code to C code and then compiling C code with the vendor-specific compiler that was available. And that's something we explicitly moved away from because on the one hand, it was fragile and it also required you to install a full-fledged compiler for your platform at hand. So we moved to using LLVM to generate code that can be consumed by the GPU backend. And again, then it comes back to the fact that nor OpenCL nor Vulkan supported that in a way that covers all of the GPU vendors that are out there. So we would have to look into this again, whether SPURV allows that nowadays, or if not, move to something like the Intel Unified Runtime to cover all of the backends with that. So again, summarized, no, OpenCL.jl currently does not work because the compilation model was not supported.
I think we have one more there in the front. Front.
Thank you. Thank you for the talk. I was just kind of wondering, how easy does this make it to work with multiple GPUs, if you have multiple GPUs available?
For multiple GPUs, there's generally two solutions. Either you use a library that does it for you, and in CUDA.jl we wrap a couple of those. For example, there's a version of cuBLAST that automatically uses multiple GPUs behind the scenes. That's fairly specific to the CUDA ecosystem. Generally, the solution is that you use multiple Julia tasks, and within each task, you use a different GPU, and that's perfectly supported. But it does require from you, the user, to manage both devices individually. We currently have no solution to generically support, say, A times B automatically executing on multiple GPUs. For that, you'd have to use the libraries that are specific to every backend. So you can do it, but you have to do it yourself.
Okay, thank you very much.
Okay, I think that wraps up. If there are any more questions, I'm sure Tim is approachable during the coffee break that we have now.
I will.
Let's give him another round of applause and reconvene later.